Okay, so you guys should be able to see my desktop with my worksheet. I'm finally getting some sunlight through the windows, it looks like. All right, so these problems are a little bit different than the ones that we've done so far. In this case, what we're going to start doing is having an object that is being ejected off of a ramp. So we're going to have something that is actually moving at an angle instead of just moving at an angle because it had some horizontal velocity. So this is going to change the way we set up our problems just a little bit. So here our problem says a metal sphere is launched with an initial velocity of 5 meters per second as it leaves the ramp. The end of the ramp is 1.2 meters above the floor. Calculate the range of the sphere. And then it says range is the horizontal displacement of the projectile. So if we have our metal sphere coming off the end of the ramp, and it says that it has a velocity of 1.5 meters per second at that angle, we're going to have to think first a little bit about our components because our object is going to have a vertical component of velocity. So here's our vertical initial velocity, as well as a horizontal velocity that we need to know about in order to be able to solve some problems. We also need to keep in mind that what this problem is telling us is that our object is going to come off the ramp and then land on the ground somewhere. And what we need to calculate is the range, the change in horizontal position. As we do this, we also have to keep in mind that if we look at this elevation where the sphere leaves, that the height of our object, so the vertical displacement is actually going to be minus 1.2 meters. We're not looking at a situation like somebody kicking a ball down a field where the ball is going to return to the same elevation it started at. Because here we see that we have a ramp where our object is going to leave the ramp above the zero position. So let's see what things we know and figure out what we're going to need to solve to be able to do this. What we ultimately are going to do is solve for a horizontal thing. We're going to be trying to find our change in position. So that's the thing that we're going to solve for. In order to be able to solve for that, we need to know the things in the equation that go with solving horizontal problems, our horizontal velocity and time. And so far, it looks like we don't know either of those things. However, we do have enough information that we'll be able to solve for our initial horizontal velocity. So that's one thing we're going to need to do. We're going to need to solve for our initial horizontal velocity. We're also going to need to solve time. So what about vertical things? Because we know that if we know enough vertical stuff that we can solve for time and use it with our horizontal problem. So we know that, I just wrote a triangle there, didn't I? It should be a triangle and a Y. There we go. And kind of fixed it. So we know that our vertical displacement is going to be a 1.2 meter drop. We can solve for our initial velocity. So that's something else we're going to have to do. Solve for our initial horizontal velocity. And then let's see, we know acceleration due to gravity is minus 10 meters per second squared. And then maybe we can solve for time. So if we solve for our velocities and then use that velocity in our vertical stuff to solve for time, then we can put time up here with our horizontal stuff, and that'll let us solve for our change in position. So let's start with our velocities. If I redraw this triangle just a little bit, where should I put it? I'll put it over here. We know that we've got our initial horizontal velocity. We've got a vertical velocity that we can add as the side of a triangle here to get our overall velocity of 1.5 meters per second. We also know that because of congruent angles that this angle is our 20-degree angle. So we know that much. So how do we solve for these? We've done a bunch of them. We know that the relationship between our horizontal velocity and this hypotenuse is the cosine of 20 degrees. So we know that, let's see, the cosine of 20 degrees is equal to our Vxi divided by 1.5 meters per second. So our Vxi is going to be 1.5 meters per second times the cosine of 20 degrees. And that if we put that into a calculator, we'll find that that's 1.4 meters per second. So I'm just going to record that over here so I know I'm starting to fill in this information. For our next one, we need to solve for our vertical velocity. There, the relationship between the hypotenuse and this side of the triangle, because it's the opposite side, will be the sine of that 20-degree angle. So now we've got the sine of 20 degrees is equal to our initial vertical velocity divided by 1.5 meters per second. So if we calculate this, it's 1.5 meters per second times the sine of 20 degrees, which is going to give us a value of 0.51 meters per second. It's a lot less than this, and that's because that angle is so short. So this side of our triangle is going to be much shorter, so that measurement is going to be much shorter. I'm going to go fill it in over here. 0.51 meters per second. They have different numbers of values after the decimals. Both of those are numbers with two significant figures, which seems reasonable to me considering that both the angle and the hypotenuse both have two sig figs. All right, so now we can solve for time. All right, this is where it gets really exciting. If we look at our equations, we see that we can solve for time if we use the equation the vertical displacement is equal to 1/2 acceleration times time squared plus our initial vertical velocity times time. So if I fill in some of those values, I've got minus 1.2 meters equals 1/2 times minus 10 meters per second squared times time squared plus our initial vertical velocity, that 0.51, 0.51 meters per second times time. Guys, I'm at this point, you know, I like when it's easy to kind of factor these out. This one doesn't look like it's going to be easy, but let's just see how this goes. If I add 1.2 to both sides, then I'll have 0 equals, I'm going to simplify this to minus 5 meters per second squared times time squared plus 0.51 meters per second times time plus, because I'm adding 1.2 to both sides, 1.2 meters. Uh-oh, guys, look, I'm not going to be able to factor that one in my head. So one of the things that we're going to have to do is remember that thing from math class when we're working with quadratic equations, this ax squared plus bx plus c equals 0. When that is the case, we can solve for x by doing this. Minus b plus or minus the square root of b squared minus 4ac divided by 2a, which looks a little bit cumbersome, but it could be worse, right? If we had to do this by guess and check, it would take us forever. So to solve for time, I'm going to say that time is equal to, oh, I'm going to go back one step. So in case you guys haven't seen this before, what this means is that we're going to use the coefficients in our equation to be able to solve for time. So our coefficients here, this one is A, this one is B, and this one is C. And they always work so that A is the one with the variable squared, B is with the variable just once, and then C is the intercept or the coefficient that doesn't have anything. So our time is going to be equal to minus 0.51 plus or minus, and I'm going to wait a second to draw my square root because otherwise I'll guess the wrong distance probably. 0.51 squared minus 4 times minus 5 times 1.2, and then that's a square root. And then that's all divided by 2 times minus 10. So the way that I was taught to solve these was to kind of figure out what this value was and then divide it up in the plus or minus. So our t would be equal to 0.51 plus or minus, and then this was 4.9 divided by, oh, hang on a second, this is a minus 10, this is minus 5. All right, then minus 10 down here. So what I would normally do, and I can't remember if I invented this trick or if a teacher showed it to me, but it works for me, so I'm going to show it to you guys, is I would just draw 2 arrows, and then I would say, okay, I need to do this once with a positive sign there, and then I need to calculate it again with a negative sign. And so I'm going to say that this one is where I calculate it with positive, and then down here is where I do it with negative. So if I do minus 0.51 plus 4.9 divided by -10, I get a value of minus 0.44 seconds. It ends up negative because this number ends up being a large positive number divided by a negative number. If I subtract the 4.9 from minus 0.51, the answer that I get then is 0.54 seconds. And so I have to choose which one I think is correct. The one that I think is correct is this positive value. And the reason for that is because if I look at my picture, I know that this is basically when time equals 0. And so if I'm going to go forward in time, which is what I intend to do, I need to have a positive number. So over here would be where time is equal to 0.54 seconds. If I wanted to know what it meant by that negative one, if I imagine I have a parabola here, back here is where time is minus 0.44. So this kind of makes sense because we know that we're not quite at the halfway point here. We're going to have our ball go up a little bit and before it comes back down. So it makes sense that the time going forward is greater than the time going backward. So I'm going to go with 0.54 and I'm going to fill that in my list. Aha, now I have enough information to be able to solve this. And I know that my change in position is going to be my velocity, 1.4 meters per second, multiplied by the time that it's traveling at that velocity. So if I calculate 1.4 times 0.54, I end up with a range of 0.76 meters. So my picture is not drawn quite to scale, right? Because if I look at this, like 0.76 meters should not be very far. But that's okay. We can still learn the things we need to learn from that picture. Does anyone have any questions about problem number 1?
Can you move the paper up a little so I can see the bottom?
Yeah, you want the equation?
Yeah, like the white bar just keeps cutting it off on the Google Meet, and I can't get it to go away. That's
Oh,
why I
I'm
couldn't
so
move it.
sorry. I can't even see that on my screen. Is it high enough now?
Yeah, that's good. Thank you.
Okay. So what I want you guys to work on today, I think that we're about halfway through the period, is I want you guys to take a look at problem number 2. And just problem number 2. I don't want you guys to go farther than that because it's a beautiful day outside and I don't want you guys to spend a ton of time at the computer. So I don't know if you guys can see it. I put a couple of notes on here for the other periods. Keep in mind that when you're doing this kind of thing, you're going to need to solve for the components. And now we have an initial velocity that is downward. So don't be alarmed by that. Just kind of roll with it. We've got the same velocity here. The angle's a little bit different. So the calculation is going to be similar. But keep in mind that you're looking for a negative value for this velocity if you were keeping upwards as positive. And then again, it asks you to solve for the range. So you could do similar things as we did in problem number 1. Figure out how much time it takes for the ball to hit the ground, and then use the amount of time that it takes to hit the ground along with the horizontal velocity to calculate what the range ought to be. And so our plan will be that we will go over that tomorrow. You guys have any other questions for me?